Good afternoon, everyone. Welcome to our last webinar in the 6-part series hosted by Rockflow Dynamics. My name is Larissa Zimmer from Rockflow Dynamics Kuala Lumpur, and today's session will be hosted by my colleague Andres Bracho, who is currently based in Rockflow Dynamics Perth. We would like to thank everyone who registered and allocated their time today to attend these webinars. The response from each and one of you has been immensely great, and we hope you've enjoyed our previous webinars as well as our last session for today. Please take note that our RFD team is currently working around the clock and will continuously strive to provide the best support we can in these trying and challenging times. Please do not hesitate to reach out to our support team for assistance. Before we begin our session, I'd like to provide a brief run-through on how to navigate yourself during this webinar session. Once you've logged on as an attendee, you will be automatically muted, and should you have any questions you'd like to ask, kindly use the window in the control panel on the side of your screen and ask away at the very end of the session. If we are unable to answer all the questions live, we will answer them afterwards and share it to you via email. This webinar session will be recorded and uploaded onto our RFD YouTube channel. Last but not least, if you have any further questions and inquiries, feel free to reach us at asktnav@rfdyn.com. This webinar series has been hosted from 6 of our worldwide support offices over the past 1 month, starting from Aberdeen, Kuala Lumpur, Houston, Calgary, Moscow, and Perth. Today, we are tuning in from Perth, Australia. In today's webinar series, we will demonstrate you each stage of the integrated workflow that's available in tNavigator. If you're interested to learn more on our modules, do not hesitate to get in touch with our teams and be more than happy to assist. Before we begin today's session, I would also like to highlight that the new object modeling for faces modeling is now available for tNavigator 20.1, which is our latest and newest release update. Today's topic will be focused on Network Designer. Surface facilities can have a big impact on how a field is developed. tNavigator's network functions will allow engineers to generate integrated assets models to analyze the effect of surface facilities on the reservoir. This webinar session will go over tNavigator's integrated modeling approach and show you how to build an integrated asset model. Without further ado, let's begin today's session. Thank you, Andres.
Brilliant. Thank you very much, Larissa. Good day, everyone. I hope everyone's doing well and keeping safe and healthy in these very interesting times. Thank you very much for making the time to listen to us. I know most of you probably made the big trek to your living rooms or to your home offices, so we appreciate the effort. As Larissa said, my name is Andres Bracho. I'm part of the RFD team here in Perth, Australia. And on this 6th and last webinar of the series, we will be showing you some of the cool things we've been working on with regards to the surface facilities and also integrated modeling as a whole. So just bear with me. I'm just going to change the screen. Perfect. So, when we talk about an oil and gas asset, we are talking about a lot more than just the subsurface. I mean, sure, obviously the reservoir is at the heart of the asset, but there's another very important element that sometimes gets neglected, and that is the surface facilities. Now, surface facilities can include things from the wellhead, chokes, pipelines, separators, pumps, compressors, sealing points, tying in points, pretty much everything that you see that is on the surface. And the thing is that each one of the elements can have a significant impact on how a field is developed, how a field behaves, and how it performs. The pressure drop throughout your system, for example, determines your production and whether or not you need compressors. The processing capacity of your separator, oops, sorry about that, just bear with me. The processing capacity of your separator, the processing capacity of the capacity of your pipelines will determine how much you can put through your system, and the target production will in some way depend, or in one way or another, on the demand of the product and the scheduling of the product. Now, for this reason, for assets where the surface facilities go a little bit beyond a simple surface separator and some pipelines, it is actually very important to consider the effect that the surface can have on a reservoir. Now, seeing as you're here today, you probably heard about this sort of thing before, integrated asset modeling, integrated production modeling. Now, these are all terms used to describe the modeling and simulation of a system, which includes elements of both the surface and subsurface. However, the thing is that most of these approaches that are utilized nowadays suffer from one major drawback, and that is that sometimes it can be unbearably slow. To explain why this is so, I just want to paint a picture on how usually integrated modeling works. So on one side, we've got the surface facilities, which are represented by the network solver. So the network solver takes care of calculating what happens to the fluid and the pressure as it goes through the wellheads, pipelines, pretty much everything that you have on the surface. On the other side, we have the reservoir, which is represented by the reservoir simulation. Now, we know this very well. It's essentially the calculation of how the fluid moves through our reservoir. And in order to actually calculate this integrated model, in order to actually make sense of it and simulate it, we need to pass some information from one part of the system into another. So from the surface, we need to provide some information to the reservoir in the form of back pressures and any constraints and limits that our surface facilities may impose. And from the other side, we got the reservoir needs to provide some information to the surface in the form of inflow and how much of the reservoir fluid is going to come into the well. So in order to facilitate this transfer of information, what usually happens is we have this third element, which is called a controller. And the job of the controller is to actually pass this information and to connect both systems together. Now, this is an approach that we like to call a legacy approach. And the problem with this is actually fairly obvious. Like if you look at this picture, you can start seeing that this transfer of information from one into the other, actually it's not very efficient. We are relying on a third program to kind of pass information. We're solving these two programs, these two parts of the equation, we're solving them separately. And we're also constraining how much information can pass from one into the other. Now, on top of that, the other problem is that when we do this sort of legacy approach, what happens is we usually end up using programs that have been developed by different entities. So they can have different structures, different languages, and that on its own can bring some issues with regards to connectivity and with regards to overheads. So whilst we do provide the tools to build this so-called legacy approach, we also have our own approach that tackles this inefficient transfer of information and inefficient way of solving through integration, which is pretty much what we talked about throughout this whole series. So with tNav, we're actually in a very lucky and advantageous position. You see, tNavigator is one of the only complete hydrocarbon simulation platforms that has been developed from the ground up under the same infrastructure, same team, same language. What this means is that we don't have the communication overheads that are usually pervasive in some other platforms. So how is our approach different? Well, in our approach, rather than solving these elements separately and using a controller, we make advantage of our integration and solve both of these elements in one single system of equations with a fully implicit solver. So rather than solving the system separately and relying on the controller to make them communicate, we're actually solving these two elements together and making them work in one system. This is actually quite impressive. It means we actually have significantly faster and more stable simulations. So when we're building one of these models, we're actually bringing together a lot of different elements. So we have the two elements that we've discussed so far. We've got the reservoir, the subsurface, which essentially the calculation of the fluid movement on a reservoir. On the other side, we have the surface, which is essentially the calculation of what happens to the fluid as it goes through all the surface facilities. Now, sitting between these two, we actually have two other elements that are very important and critical. One of them is the wells, and the wells are very important because they describe what happens to the fluid as it goes from the reservoir into the surface. So in some ways, it provides a link between these two elements. The other element that's very important, and one element that without which no model would be complete, is of course the fluid, which we can represent through PVT. So throughout a demonstration that we'll do in just a second, we'll see how to actually develop each one of these elements. And as part of our integration motto, we want the creation of the system to be as seamless and as straightforward as possible. As such, we've done a lot of work to make this workflow practical and easy to use. So without further ado, let's actually have a look at how this system looks and how we can actually build one of these models. So over here, I've got a small reservoir model. And what we want to do is we want to create an integrated model. So we want to tie this to some surface facilities, and we want to model and see what sort of effect our surface facilities can have on our production. So what we do is we simply go and open one of our integrated projects. You'll see a lot of work has been done into this integration. So you'll see you can work seamlessly within interfaces. You don't have to worry about being on one specific area or another. So what I have here is a blank project of network, and we're going to start building. Just to introduce you a little bit to the interface, if you played around with tNavigator before, you will be somewhat familiar with what is happening here. So on the left-hand side, we've got a panel that allows us to move through several elements. The middle panel allows us to give us settings and allows us to have extra options for what we're building on. And on the right-hand side, we have our visualization, which is essentially where we build our model, we look at our results, we look at what's happening within it. So what we're going to do is we're going to build a very simple surface structure, and just to show you how easy it is. So on the middle panel, you see all these sort of symbols, and these are all the objects that are available to build your models. So we have, for example, sources, which is essentially just an inlet point into your well. Another inlet point can be a well. You also have sinks, which represents an outlet point of your system. So this represent the beginning and the end of your systems. Then we got things like compressors, we got chokes, we got pumps, we got your two-phase and three-phase separators, we got a gas lift element, we got automatic pumps and compressors, which allow you to ramp up your activity within them, depending on some specified limits. We've got ways of linking those elements, for example, links in pipes. Pipes allow you to describe pressure decreases or pressure differences throughout them. And for anything that might not be here, there's actually this sort of a very interesting symbol, which is actually, for those eagle eye people, is actually the Python symbol. And what this allows us to do is actually create our very own node with its very own behavior using the Python. So what I'm going to do is I'm going to build a very simple model. Let's introduce some wells first. So to introduce a model, it's very simple. It's just clicking on the symbol you want to introduce and adding it to the workspace. So now we can see we've got a well in there. If we want to add multiple, that's very easy. We can very simply hold the button and we can very easily introduce other objects into it. So let's build this model. Let's add then some chokes for each one of our wells. Here we go. And let's make a manifold. So let's join them all at the joint. So we add a joint in here. Very simple system. So let's imagine this is a gas and water system. So we're going to do a two-phase separator, put it in here. And finally, we're going to have a compressor for the gas side and two outlets. So one for the gas and one for the water. So now we've introduced our systems, our nodes. It's time to actually link them together. To link them together is also very simple. We can select either links or pipelines. So if I select a link here, you can see very easy how to connect two different nodes. Let's actually introduce pressure drops from each one of our chokes to our joints. So we can introduce a pipeline. Here we go. And the same for this, from our joint to our separator as well. And let's link the rest of our system. Now, once we have a valid system from inlet to outlet, we can see the scheme actually becomes colored, and it symbolizes that we have a ready scheme to work with. Now, let's do this final link, and we've got our system together. Now, in order to avoid you just seeing me clicking around, I'm going to use one of the oldest tricks in the book, and this is one I prepared earlier. So essentially, all we have here is a skeleton. We still haven't specified anything. We just added a couple of extra nodes just to symbolize the link with our reservoir model. So we have as many wells as we have on our reservoir model, and it's very, very similar. We have some pipelines, some joints, a two-phase separator going to a compressor, gas and water. So we are almost actually done with specifying the surface side of these things. The next thing that we need to do is actually specify the properties of each one of these nodes, because obviously we've added them, but we haven't specified what's in them. So to specify what the properties of a specific node, it's as simple as double clicking, and it brings this little window where we can specify what happens. Now, obviously, this sort of thing doing one by one might be a little bit tedious. So what we can do is we can actually specify multiple of them by selecting them, clicking on edit, and now we've got a table where we can actually modify each one of them in one. Now, if we want to add parameters for all of them together, what we can do is simply click a button, and now everything I enter in here, for example, a temperature, it's applied to all of the wells I have selected. Now, wells can be two different types. You can have a standalone model, which is essentially just running the surface with a given kind of IPR and VLP. Well, in this case, we want to do it. This is all about integration. So we actually want to communicate it with the reservoir. So what we're going to do is we're going to tell it to be, this well is going to be a simulator type, which means we're building an integrated model. So that's simple. I've added what I needed to add, and now my wells are completed. Now, I could go around and do this for each one of the nodes that I want to do, or another option is to use the workflows. So this is my workflow editor that I just pulled up. I have a workflow already built, and for those of you who had a bit of experience in geologic modeling or our model designer and our geology designer, you would be acquainted with the workflows. The workflows is essentially just a series of steps that we predetermined, and as I can then run it in batches so that it runs through all these steps that I just created before. So in here, we're actually specifying each of our node properties. And what I can do is I can simply click Run Workflow. You can see it runs through all the steps. And now if I close this and open one of my nodes, you can see now we have all the specified things that we need. So that's it. We've got the surface, we have the subsurface defined. You remember from the last slide that I showed you, it's actually 4 elements. So now the next step is to define the wells. Actually, the next step is actually to define the PVT, sorry. So let's define the PVT. To define the PVT is actually very simple. When you're working on this sort of project, you will see this, this droplet symbol in the interface. Now, it has a question mark, which means we actually haven't defined the PVT. So to define the PVT, I can simply click on this button. Now, this particular project already has a PVT, but I want to show you how to create one because it's actually quite easy. So I'm going to click on the plus button to create a new PVT project. We can name it whatever we'd like. We'll leave it as PVT project. And what this does is it takes us to a PVT toolkit, which we can use to define the fluid or the PVT properties. So this in itself is probably another topic for discussion, and we can talk days about this. However, I'm just going to give you a quick run through so you can create compositional variants, which then you can run them on compositional cases. You can create black oil cases. You can create thermal variants if you have temperature into the equation. For this particular model, the reservoir model that we have is a black oil model, and we already defined the PVT in there, so we're going to utilize that particular PVT that we've already defined. So to do that, it's very simple. I don't have to redefine anything. All I have to do is import the properties that I've already done for my reservoir model. So I can click here, import, and the model that we have is actually an E1 format. So I'm going to click there, and just bear with me as I look for the props section of my model. So there it is, model underscore props. Open and add. And now we can see, without having to define anything, we have incorporated the properties of our model that we have already had created before. So once I'm happy with that, I can go back onto my structure here, click again on the bottom for the PVT, and then tell it to utilize the model that we just created, the model underscore props. Click the tick, and now we have defined it. You can tell that we have defined it because now we don't have a little question mark, and that is 3 out of 4 of our systems. You can see how simple that is, and we try to make it as seamless as possible so that you don't have to go back and switch between programs. So finally, the fourth and last element that we need to define is actually the wells. So to define the wells, we're going to utilize the well toolkit. So again, we can open a new toolkit by clicking this plus button. There's some wells already in here, but I'm going to show you how to create them. So let's create a new well project. Perfect. And this takes me to my well interface. So what this let us see is, the first thing that we'll see is this this particular tab, which shows us the geometry. In this case, we haven't entered anything, so it doesn't show us too much. So let's actually enter the trajectory of your well, which you should have as part of your raw data. So I'm going to import my well trajectories, and just bear with me as I find it. And we're going to do well 1. Let's click open. Load our data. So now you can see the well trajectory. It shows you in 2D, and it shows you the tabular data that we just imported. It also, if we flip to the 3D, we can see the trajectory of our well in 3D. Now, the other thing we need to do is actually describe what's within this well. So what sort of elements comprise our well? To do this, we go to the tab Well Construction. And this allows us to then define what sort of elements are within here. So let's say, for example, we want to introduce a casing. We can click on the casing symbol right here and simply drag and drop. And now we're introducing and building our actual well. So each one of these elements, you can change them by dragging and dropping, or if you have the data and you want to be precise, which probably you should, you can utilize the numbers that you have on the left-hand side. So we got our casing. Let's put some tubing in here. Let's put some, obviously, perforations. We want the fluid to come in. Let's put a packer so that we don't have annular flow. And let's put a filter down on our well. Perfect. So it's a simple, that's all you need to do to define your wells. Obviously, depending on the complexity of your wells, you probably spend a bit more time on this, or if you have other wells, you can actually duplicate this particular construction and then edit it so that your work becomes a little bit easier. Now, the last step, and the reason that we need to define these wells, is because we need to define the pressure drop that happens in the well. So we need to actually define a VFP table. To define a VFP table, it's very simple. We click on plus and we calculate the VFP table. And obviously we've got the well construction, but we also need to tell it which sort of fluid is going to that well in order for it to know what sort of pressure decrease is going to happen. So in here, when we click to build the VFP prod table, it gives us some PVT projects that we've already made. You can choose to add another one, but in this case, it's the same fluid. So we're going to utilize the exact same one that we had before. Everything is reutilized. We click on set. And we can define different correlation parameters, like for example, which correlation to use for the pressure drops for which part of the well, what classifies as a deviated and as a horizontal well, and we can even tell it which points to use for the table that we're going to create. Once we're done with that, we simply just click OK, and you can see how easy it is to create your VFP tables. So I can go back to my project, and once we have defined our wells, we're pretty much ready to run this model. Now, we just did well number 1. I've already done well number 2, 3, 4, and the rest of the wells, so that you don't have to see the procedure again. However, it's very simple. If you have wells that are quite similar, again, you can duplicate this VFP project that you made and utilize this duplicated projects to attach to your wells. Or if you've already done the work and if you already define your VFP table, what you can do is simply import the VFP table that you already created and use that as your main well model as well. So we're almost ready to run. The last thing we need to do is we need to tell it which projects to use, because as part of this envelope that we've created, we can have a lot of data. There's no limit of data that we have. So in order for us to run it, we need to tell it which particular sets of data we're going to use. And to do that, we are going to first assign the VFP tables that we've created to the wells. So I'm going to click on VFP to network objects. Again, we can see all of our wells are mapped. You can see they all assign a VFP, except for well number 1, which is the one that we just created. So I'm going to tell it to use the VFP we created before, which is this one. Perfect. Now you can see it has a little symbol, and it means that we're ready to roll. The very last thing we need to do is to create a case. And a case is essentially a tool that allows you to create kind of scenarios for you to run different things. In this case, we only really have one particular case. So what I'm going to do is I'm going to select for the scheme or the structure that we have, we're going to select the one that we've been working on, which if you can see up here is called structure only. We're going to select for the wells, we're going to select the one that we just did, the VFP project. And for part of the PVT, we're going to utilize the PVT project we just created as well. So we've selected them. We can close this, and actually we're ready to run now. So I'm going to save my project, which is very important. And in order to run our project, we can very easily go back onto our Reservoir model. And let's actually reload this model so that everything applies to it, everything that we've done. And to run the model is as simple as you'll be very acquainted with this button. We just simply need to click run. And you can see it starts running, it starts giving us some information, and it starts running our very own integrated model. So you can see how in just a matter of clicks, we actually build all 4 systems. It was actually fairly straightforward. Obviously, these are small models, but it's not much more difficult to create a big one. Now, whilst this is simulating, I just want to show you very quickly how we are actually linking the surface and subsurface. So I'm going to go very quickly into Files and show you the data deck that I have here. So here it is. Here's the data deck. It's the text file that describes our reservoir. And the only thing that we need to do to define the integrated project and to link both of our models is this keyword that's called import project. As soon as tNav reads it, it knows that we're talking about an integrated project. Then we just specify the directory for the particular network project that we have. And the case, which as we saw before, we only have one case. So in this case is case 1. So well, this actually it's simulated already. So we can actually go ahead and look at some results. So to view results, we can then open our model again. And what you see here, we've got our structure that we had before. We can see now there's little circles which actually tell us, this is what we call bubble maps, and it actually tells us some parameters about what's happening at a specific time step. You can see the time step slider is up here, and it's as the results are being simulated on the reservoir, they're actually being updated on this side as well. Now, the bubble maps can show you pretty much anything you're interested on. So for example, right now they're showing us pressure, but we can, for example, tell it to show us mass of the, let's see, gas rate, and we can see where our gas is actually going. We can see that our separator is doing some work and it's actually sending it, most of it through our gas sink. Now, there are other sorts of results that you can visualize as well. We can, for example, look at the objects. So it's the next tab over, which gives us some preliminary information at a specified step about all of our nodes. So on the columns here, on the rows here, sorry, we're having all of the nodes that we have on our system. On the columns, we're having some parameters that we can select from our middle panel. So I can select, for example, gas mass rate, liquid mass rate, so on and so forth. We also have results in branches and pipes, which is kind of allow you to traverse through some of the systems that we've had. So branches are a connection of 3 different nodes. And you can see here, I can join, for example, from joint 1 to pipe 2 to well 22, we can see how things change. So in this case, we're visualizing the mixture mass rate and the pressure, but you have available a list of different things that you can show for each one of them. There's also pipes, which is pretty much the same, but it's the traverse through a pipe. So you can very much specifically see what's happening within your pipeline, how things are changing, how the pressure affects throughout the pipeline, so on and so forth. And the last one, and probably the one that you would be most used to, is the graphs. So the graphs kind of center around a specific node, and it show you what happens through time. So on the x-axis we have time, on the y-axis we have whatever properties we have selected. The cool thing about this is that you can do so interactively through different views. So we can, for example, put our graphs down here, put our network up here, and let me get rid of this so it makes a bit more sense. And now we actually have an interactive plot, so I can be clicking on each one of our nodes and we can be visualizing all of our results as we're seeing simulated through. So hopefully that gives you a bit of an idea of what a network designer is in a nutshell, how we're actually tackling this efficiency problem and how we are trying to change the way things are done. So I know some of you might have some questions. So if you have any questions, please feel free to ask them now. Larissa, I'm not sure if you have some words as well to finalize.
Yeah, well, we have a few questions here that I can ask. And
Okay, brilliant.
like we begin? Yeah, okay, great. Okay, so question number 1, can you have multiple fluids with different PVD properties go into the system?
Okay, that's actually a very good question. Okay, let me just go back to our system here. That's an excellent question. Yes, the short answer is yes, you can. So in this particular exercise, we actually had one very simple kind of black oil module. So we only utilize one PVT, but you can very easily have multiple PVTs. You can actually have multiple black oil models connected to it. You can have multiple compositional models connected to it, and you can even have black oil and compositional models feeding into one surface model. The way we tackle that is through what I showed you before, which is the PVT project. We can define our variants here, and we use an approach similar to what you would know as a common EOS or equation of state, where we define the mixture of the fluids into one equation of state, which then allows us to define them into one. Hopefully that answers the question.
All right. Very, very insightful, Andres. We have another question here. Let me
Sure.
open them. Okay. Can we do group editing to pipeline?
Yes, we can. So it's a similar approach that we saw before. So we can select multiple of them and simply click edit, and we can do we can actually edit all the inputs as a group. Again, if you have the same pipeline for different nodes, what you can do is simply click on the modify all, and then it will allow you to then define the same parameter for all of them.
Okay. All right.
I actually have
Sorry.
one that's that looks very interesting. Sorry, Larissa, to cut you off. I've had I see a question that is actually quite interesting that I'd love to reply as well.
Yeah, go ahead.
So someone asked, can you make changes to the model objects throughout the simulation? And I'm actually glad someone asked that question because it's something that I didn't have too much time to cover in here. So yes, in this particular case, all of our surface is remaining static. So we actually don't have any changes after we've defined them. However, it's actually, you actually have a lot of systems that change throughout the life of your reservoir and the life of your operation. And to do that, to tackle that, we have this this thing called an events editor. So the events editor, what it allows you to do is specify how things change in each one of your nodes at a specific point in time. So if I, for example, have changes in how my compressor behaves, or if I have different stages that I want to kind of hard code into here, we can very easily just put our date, put our different the parameter that we want to change, and these changes would be reflected on our model.
All
Hopefully that
right.
answers that question too.
Okay, thank you, Andres. So we have a few, I mean, we have a lot of questions coming in, but since we're short on time, fret not, we will answer them accordingly after the session, and we will email it to you. So thank you very much, Andres, for that insightful presentation. Just
Thank you, everyone.
take note that our session today will be uploaded on our RFD Europe YouTube channel. And we would like again to thank you everyone for joining today's session. There will be a short survey for you to provide your comments at the very end of this. Till then, we hope you've enjoyed the session and we look forward to hosting our next webinar series in the nearest future. Take care, everyone, and stay safe.
Thank you. I think we will leave the presentation up for a little bit longer, just in case there's anyone with any extra questions, so we can tackle them at the end as well. So we'll leave this on for a couple more minutes just to give everyone a chance.
Okay.
Perfect. Thank you, everyone.